Welcome. You have nowhere to be and nothing to do. Let your body settle into wherever you are resting. Let your breathing slow and allow the events of the day to drift gently away. Tonight we are going to travel together across the full sweep of time, from the very first moments of our galaxy's birth to its quiet disappearance far in the future. All you need to do is listen and rest. The Milky Way formed roughly 13.6 billion years ago from vast, slowly drifting clouds of primordial gas. In the very early universe, enormous regions of hydrogen and helium, the simplest elements born in the first moments after the Big Bang, began to cool and pool together under the patient pull of gravity. Over hundreds of millions of years, these clouds gathered themselves inward, turning and condensing, until something recognizable as a galaxy began to take shape. The first stars in the Milky Way ignited within a few 100 million years of the Big Bang. These earliest suns were enormous by today's standards, brilliant, hot, and short-lived. They blazed to life inside the densest pockets of those ancient gas clouds, and their light was the very first starlight our galaxy ever produced. For a brief time, they were the only lights in an otherwise dark and formless universe. The Milky Way's oldest stars contain almost no heavy elements, forged long before supernovae enriched the galaxy. When those first great suns exhausted their fuel and exploded, they seeded space with heavier atoms, carbon, oxygen, iron. But the stars that formed before those explosions knew none of that richness. They were made of almost nothing but hydrogen and helium, the bare ingredients of a newborn universe, and astronomers can still find a few of these ancient survivors drifting quietly through our galaxy today. Ancient globular clusters orbiting the Milky Way are relics from the galaxy's earliest assembly. These tightly packed spheres of hundreds of thousands of stars formed in the first billion years of the galaxy's life, and they have been circling ever since, loyal, unhurried companions tracing wide paths around the galactic center. When you look at a globular cluster, you are looking at a structure that was already ancient when the solar system was born. The Milky Way built much of its mass by drawing in smaller dwarf galaxies over billions of years. Gravity is endlessly patient, and over cosmic time our galaxy has pulled countless smaller neighbors into itself, absorbing their stars, their gas, their dark matter. Each of these smaller galaxies surrendered its identity slowly, its stars becoming part of the Milky Way's growing body. It is a quiet, unhurried kind of transformation, taking place across timescales no human mind can truly hold. The Sagittarius dwarf galaxy is currently being shredded and absorbed by the Milky Way. This small companion has been orbiting our galaxy for billions of years, and with each pass it comes closer, its stars pulled loose by the Milky Way's immense gravity. Scientists believe it has already looped around us several times, growing more diffuse with every orbit. Its stars are not vanishing, they are simply becoming part of us. Streams of stars from past mergers still trace luminous arcs across the Milky Way's outer halo. Long after a smaller galaxy has been absorbed, its stars leave behind a kind of memory, a faint ribbon of light curving through space, marking the path the old galaxy once traveled. These stellar streams are nearly invisible to the naked eye, but astronomers have mapped them with sensitive telescopes, reading the history of ancient collisions written in the positions of stars. The Large Magellanic Cloud is the Milky Way's largest current satellite galaxy, about 160,000 light-years away. Visible from the southern hemisphere as a soft, hazy patch of light, it looks to the naked eye like a piece of the Milky Way that has drifted free. It is a small, irregular galaxy, rich with young stars and glowing nebulae, and it has been accompanying our galaxy for billions of years, a faithful, luminous companion in the southern sky. The Magellanic Stream is a ribbon of gas stretching 300,000 light-years behind the two Magellanic Clouds. Invisible to the naked eye, but revealed by radio telescopes, this enormous trail of hydrogen gas marks the path the Magellanic Clouds have carved through space. Scientists believe it was drawn out of them by the Milky Way's gravity over billions of years of close interaction. It is one of the longest structures associated with our galaxy, a quiet, invisible wake trailing through the dark. Let yourself settle a little deeper now. There is nowhere to be, nothing to hold on to, nothing to figure out. Let your shoulders release. Let your hands rest open and still. With each slow breath, the thoughts of the day grow a little more distant, like lights fading at the edge of a long, dark road. You are here, you are safe, and all you need to do is drift. The Milky Way currently holds between 100 billion and 400 billion stars within its spiral arms. That range itself speaks to the immensity of the galaxy. Even our best instruments cannot pin down an exact count. Each of those stars is a sun in its own right, many of them circled by their own worlds. The number is so vast, it dissolves into something almost like silence. Our galaxy's disk stretches roughly 100,000 light-years from one edge to the other. To cross it traveling at the speed of light, the fastest anything in the universe can move, would take a full 100,000 years. And yet, seen from far enough away, it would appear as a delicate, flattened spiral, thin as a wafer, compared to its width, turning slowly in the dark. Across the center of the Milky Way runs a long bar of stars, stretching approximately 27,000 light-years from end to end. This stellar bar is not a rigid structure, but a slowly rotating concentration of billions of stars, channeling gas and dust toward the galactic core. Our galaxy is what astronomers describe as a barred spiral, a shape that gives it a quiet, balanced elegance when seen from above. At the very heart of the Milky Way rests a supermassive black hole carrying the mass of 4 million suns. It sits at the center of everything, unseen but felt, its gravity anchoring the inner regions of the galaxy, the way a deep, still weight holds everything around it in place. Scientists have imaged the region surrounding it, revealing a glowing ring of superheated gas orbiting the darkness at its core. The Milky Way rotates as a whole, and our Sun takes approximately 225 million years to complete a single orbit around the galactic center. This vast circuit is sometimes called a cosmic year. In the entire history of complex life on Earth, the Sun has completed only a handful of these immense loops. Right now, as you rest, it is moving through the galaxy at extraordinary speed, and yet the night feels perfectly still. Surrounding the Milky Way is an invisible halo of dark matter, a substance that emits no light and interacts with almost nothing, and yet outweighs all the visible stars, gas, and dust in the galaxy by roughly 6 to 1. We cannot see it, touch it, or detect it directly. We know it is there only because of the way it bends the paths of stars and holds the galaxy's arms from flying apart. It is the quiet, hidden architecture beneath everything. The Milky Way does not travel alone through the universe. It belongs to a family of more than 50 galaxies, called the Local Group, all bound together by gravity, across a region of space roughly 10 million light-years wide. Some members are large spirals like our own. Others are small, faint dwarf galaxies, barely visible even to our best telescopes. Together they form a loose, unhurried community drifting through the cosmos. The nearest large galaxy to the Milky Way is Andromeda, lying 2.5 million light-years away. On a clear, dark night, it is just barely visible to the naked eye, a faint, smudged glow in the constellation of the same name. The light entering your eyes when you find it tonight left that galaxy, long before our earliest human ancestors first walked the Earth. It is the most distant thing a human being can see without any instrument at all. Andromeda is somewhat larger than the Milky Way and holds roughly 1 trillion stars within its spiral arms. Where our galaxy may contain up to 400 billion suns, Andromeda carries more than twice that number, spread across a disk even wider than our own. It is our nearest large galactic neighbor, our companion across the void, a vast island of light moving steadily, unhurriedly, through the dark toward us. At the heart of Andromeda rests a supermassive black hole, massing about 100 million times the weight of our own Sun. That is roughly 25 times more massive than the black hole at the center of our own galaxy. It sits there in absolute stillness, invisible, drawing light and matter into itself across millions of years. 2 galaxies, 2 immense dark hearts, each one a point of profound, unhurried gravity at the center of its own vast world. Let your body settle a little more deeply now. There is nowhere you need to go, nothing left to hold. Allow your shoulders to release, your jaw to unclench, your hands to rest open and still. Each breath arrives on its own, slow and full, and leaves just as easily. You are safe. You are warm, and the night is holding you gently. There is only this moment, and the quiet that fills it. In the year 2012, astronomers announced a finding that had long been suspected but never fully confirmed. Andromeda is on a direct collision course with the Milky Way. Using decades of careful observation, they traced the galaxy's path through space and found no ambiguity. The 2 galaxies are headed toward each other, not drifting, not wandering, moving with slow, certain purpose across the immeasurable dark between them. The confirmation came through the extraordinary precision of the Hubble Space Telescope, which spent years measuring the tiny, almost imperceptible sideways drift of Andromeda's stars across the sky. These measurements, called proper motions, allowed astronomers to map the galaxy's exact trajectory through space with remarkable accuracy. The numbers left little room for doubt. Andromeda's path was clear, its destination written in the slow geometry of gravity. Even now, Andromeda is drawing closer to us at roughly 110 kilometers per second. That sounds tremendous, and by human measures it is. Yet on the scale of intergalactic space, it is the most unhurried of approaches. 2.5 million light-years still separate us. At this pace, the journey will take billions of years to complete. The universe moves on its own timescale, vast and unbothered, indifferent to urgency. The first close encounter between the Milky Way and Andromeda is predicted to begin in about 4.5 billion years. That span of time is almost impossible to hold in the mind. It is longer than the entire age of our solar system. It is longer than the time it took for life on Earth to evolve from its earliest single-celled ancestors to every creature alive today. The merger ahead is not an event in any human story. It belongs to a chapter of time beyond imagining. Nearby, in the local group, a third significant galaxy watches from the wings. The Triangulum galaxy, a graceful, loosely wound spiral, is the 3rd largest member of our galactic family. Smaller than both the Milky Way and Andromeda, it drifts in their vicinity, bound to the same gravitational story. Scientists believe it may be drawn into the merger as well, a quieter participant folded into the slow, immense dance of the 2 larger galaxies. It is natural to imagine a collision of galaxies as something violent and shattering, but the reality is far more serene. The stars within each galaxy are separated by such enormous distances that the chance of any 2 stars actually striking each other is extraordinarily small. When galaxies collide, they pass through each other like 2 clouds of fireflies drifting together in the dark. The stars themselves barely notice. It is gravity, not impact, that reshapes everything. What will be dramatic, though, is what gravity does to the shapes of the galaxies themselves. As the two vast structures draw close, gravitational tides will stretch and pull at their outer edges, drawing long arching streams of stars out into intergalactic space. These tidal tails can extend for millions of light years. Gossamer threads of suns cast adrift into the void. We can see this happening in other colliding galaxies across the universe, glowing bridges of starlight flung between worlds. The first detailed computer simulations of the Milky Way and Andromeda collision were completed in the early 2000s. Astronomers fed in the masses, velocities, and positions of both galaxies and watched the future unfold across their screens in slow motion. Frame by frame, the simulations revealed the graceful, drawn-out choreography of the merger. The slow approach, the first distortion, the long arcing tails, the gradual blending of two galaxies into one. It was the first time humanity had truly seen its own distant future written in light. NASA's 2012 simulation predicted the merger would be largely complete within about 6 billion years. Scientists ran the most detailed models yet produced, weaving together the masses and motions of both galaxies into a single, slowly unfolding story. The result was a timeline, vast and unhurried, in which two spirals dissolve into one over billions of years. 6 billion years is a span so immense it is almost impossible to hold in the mind, and yet it arrives eventually, as all things do. As the galaxies draw closer to one another, their mutual gravity will begin reshaping them long before they ever touch. The outer edges of each disk will feel the pull of the other's mass, and slowly, gracefully, they will be drawn outward into sweeping tidal arms, great curving rivers of stars, arching away into the dark. These arms are not violent eruptions but slow, majestic deformations, the way a tide reshapes a shoreline over centuries. The light from those arcing star streams will travel for millions of years before reaching any eye. Let your body settle a little more deeply now. There is nowhere to go, nothing to hold on to, nothing that needs your attention tonight. Let your shoulders release. Let your hands rest open and still. With each slow breath, feel the day growing more distant, like a shoreline fading behind a boat drifting out to sea. You are safe and unhurried, and the only thing asked of you right now is simply to rest. Let your thoughts thin and loosen. Let them drift. About 3.75 billion years from now, Andromeda will have grown so large in our sky that it will span a width greater than 20 times that of the full moon. Imagine standing beneath that sky, not a small oval smudge near the horizon, but an enormous luminous structure filling a vast arc above you, its spiral arms faintly visible to the naked eye. It will be one of the most extraordinary sights any sky has ever offered. The light entering your eyes from that galaxy will have left it before our earliest human ancestors ever walked the Earth. The Milky Way and Andromeda will not simply collide once and merge cleanly. Scientists believe they will make 2 or 3 close passes, sweeping through each other, pulling apart, and falling back together again over the course of hundreds of millions of years. Each pass will reshape and distort both galaxies further, drawing them into an ever more tangled embrace. It is a slow orbital dance of gravity, patient and inevitable, each return drawing the two structures a little closer to their final, inseparable union. During that first close passage, the Milky Way's spiral arms, those graceful, slowly rotating structures we think of as defining our galaxy's shape, will be pulled apart and disrupted. The orderly pinwheel pattern that has persisted for billions of years will begin to unravel, its arms stretched and scattered by the gravitational influence of Andromeda sweeping past. What was once a delicate, symmetrical structure will become something wilder and more diffuse, not destroyed, but transformed, the way a reflection on water is stirred by a passing breeze. As the two galaxies pass through each other, their vast clouds of gas and dust will be compressed by powerful gravitational shocks, Wherever gas clouds are squeezed together, the conditions for new stars to form will suddenly be met, and star formation will surge dramatically. Regions that were once quiet and dark will erupt in brilliant nurseries of newborn suns, blazing blue and white against the chaos. It is one of the great paradoxes of galactic collisions. Out of disruption comes an extraordinary flowering of new light. We do not have to imagine what the colliding Milky Way and Andromeda will look like during their most active phase. We can simply look outward across the universe and find galaxies already living through that moment. Starburst galaxies, blazing with the light of millions of newly formed stars, show us exactly what our own galactic collision will resemble at its peak. They are radiant and turbulent, lit from within by waves of stellar birth. They are, in a sense, mirrors held up to our own distant future. One of the most vivid previews of our own fate can be found in the antennae galaxies, two spiral galaxies currently in the midst of their own collision, millions of light-years from here. Their long, sweeping tidal tails curve outward like the antennae of an insect, giving them their name. Their interiors blaze with furious star formation. They are not a warning or a cause for alarm. They are simply a glimpse, offered to us now, of the slow and luminous transformation that awaits our own sky in the deep future. During the long, tumultuous passage of the two galaxies through each other, our own sun will be subject to the shifting gravitational landscape around it. Scientists have calculated that there is only a small probability, a few percent at most, that the sun would be flung outward from the merger entirely, cast into the cold darkness of intergalactic space. It is possible, but unlikely. The sun, in all likelihood, will simply be carried along, its orbit reshaped, its neighborhood altered, but its journey continuing, unhurried, through whatever the galaxy becomes. Most solar system models predict that the sun will survive the entire merger and be incorporated into the new combined galaxy. It will not be destroyed, not extinguished, not cast away into the void. It will simply continue, its orbit reshaped by the vast gravitational reshuffling, its neighborhood transformed beyond recognition, but its warm, steady burning unchanged. The sun, as it has done for 4.5 billion years, will go on giving light. Astronomers have given the future combined galaxy an informal and rather endearing nickname, Milky, or sometimes Milkdromeda. It is a gentle blending of the two names, Milky Way and Andromeda, folded together into one word, just as the galaxies themselves will one day fold into one. Scientists use it with a kind of quiet affection. It is a name for something that does not yet exist, offered patiently across billions of years. Milky is expected to resemble not a spiral galaxy, but a giant elliptical one, a vast, smoothly rounded cloud of stars with no sweeping arms, no rotating disk, no defined structure. Elliptical galaxies have a quiet, settled quality to them, like embers that have long since stopped crackling. They are among the largest objects in the universe, ancient and unhurried, their light a warm amber glow spread evenly across the dark. Let all of that settle now, quietly, like dust drifting down through still air. There is nothing you need to hold on to, nothing you need to remember. Let your body grow heavier, let your thoughts thin out, like mist at the edge of a field. Breathe in slowly, and breathe out even more slowly. You are safe, you are still, and the universe is doing all of its slow and patient work without any need for you to watch. Simply rest. Elliptical galaxies lack the rotating gas-rich disks that give spiral galaxies their graceful arms and their capacity for ongoing star formation. Without that reservoir of swirling, cooling gas, there is nothing to collapse into new suns. The arms of a spiral are, in a sense, the galaxy's nurseries, and when those arms are gone, the nurseries close. What remains is still magnificent, still vast, still luminous, but it belongs to a different, quieter chapter. After the merger, most of the gas available for building new stars will have been consumed in the great bursts of star formation during the collision, or expelled outward into intergalactic space by the energy of those same blazing stellar nurseries. The raw material will simply no longer be there. What was once a galaxy breathing in and out, drawing in gas, forging stars, releasing light, will settle into something more like stillness, its creative work largely done. At the heart of each galaxy lies a supermassive black hole, one at the center of the Milky Way, one at the center of Andromeda. When the two galaxies merge, these two immense objects will not immediately collide. Instead, they will find themselves orbiting each other at the center of the new combined galaxy, drawing gradually, inexorably closer over an enormous span of time. Their slow spiral inward is one of the most majestic dances in the universe. As the two black holes orbit each other, they radiate gravitational waves, invisible ripples in the fabric of space-time, spreading outward at the speed of light. Each ripple carries away a small measure of the energy that keeps the black holes in their orbit. Over millions and then billions of years, this slow bleeding of energy draws the two black holes closer and closer together, tightening the spiral with a patience that is almost impossible to comprehend. The light entering your eyes tonight left the galactic core before the first humans ever looked up at the sky. Billions of years after the galaxies themselves have merged, the two black holes at their shared center are predicted to finally spiral together and merge into a single, ultramassive black hole, one of the most extraordinary objects that will ever exist. It will be vaster than either of its predecessors, a singular point of incomprehensible gravity sitting at the heart of Milky, surrounded by the slow, cooling light of ancient stars. The merger will be complete in every sense. When two supermassive black holes finally merge, the energy released as gravitational waves would surpass any other event in the observable universe. Not the explosion of a star, not the collision of neutron stars, not any burst of light or fire. Nothing comes close. And yet this titanic release of energy would be entirely silent and invisible to ordinary senses, rippling outward through space-time itself, felt only as the faintest trembling in the geometry of the cosmos. Power beyond all imagining, expressed in perfect, unreachable stillness. Magellanic Clouds, those two small companion galaxies that have drifted alongside the Milky Way for so long, will not be spared the upheaval of the merger. The enormous gravitational forces unleashed as the Milky Way and Andromeda collide may fling the Magellanic Clouds far out into intergalactic space or draw them inward to be absorbed entirely into the body of Milky. Either way, their long companionship with our galaxy will come to a quiet, unhurried end. Long before the galaxies complete their merger, the Sun itself will have changed in ways that touch everything much closer to home. Over billions of years, stars naturally brighten as they age, and the Sun is no exception. By the time Andromeda draws near, our star will be noticeably more luminous than it is tonight, warming the Earth beyond what living things can easily endure. The merger of galaxies and the aging of our own star are two vast, unhurried processes unfolding side by side. In about 5 billion years, the Sun will exhaust the hydrogen fuel at its core and leave the main sequence, the long stable phase of its life it occupies today. As the core contracts and the outer layers swell, it will expand into a red giant, growing large enough to engulf the inner planets. Its surface will cool to a deep amber red, and it will shine with a ruddy, enormous light across what remains of the solar system, a breathtaking transformation written into the physics of every star. Long before the Sun swells into a red giant, Earth's oceans will have already quietly disappeared. As the Sun steadily brightens over the coming billions of years, the warmth reaching our planet will gradually exceed what the oceans can hold. The water will evaporate into the atmosphere and eventually be lost to space, leaving behind a dry, still world. The blue planet we know today will have become something entirely different, transformed not by any sudden event, but by the slow, patient brightening of our star. There is no need to hold any of this in your mind right now. Let it all drift away. The stars, the galaxies, the slow turning of deep time. Feel the weight of your body settling, your shoulders releasing, your breath moving in and out without any effort at all. You are here, resting, safe and still. The universe will continue its long, unhurried story without you needing to follow along. For now, there is only this moment, this breath, this gentle dissolving into rest. After the long turbulence of the merger has finally passed, Milky will settle into a new kind of stillness. The tidal arms will have faded, the starburst fires will have dimmed, and what remains will be a vast, smooth elliptical galaxy, no longer a spiral, no longer two, but one unified structure glowing with a steady, unhurried light. Its stellar population will be ancient and slowly fading, like embers in a hearth that has burned long and well, radiating a warmth that asks nothing and hurries nowhere. As Milky ages, its light will shift in color. The brilliant blue-white stars, the most massive and short-lived, will have long since burned out and scattered their elements into space. What remains will be older, cooler stars, deep orange and amber and red, glowing with a mellow, autumnal warmth. The galaxy will look nothing like the Milky Way we know, with its bright blue spiral arms. Instead, it will glow like a slow, steady fire, rich in color, patient in its dimming. New stars are born from clouds of gas and dust, and Milky will have very little of either left. The great reservoirs of raw material that once fueled star formation across both galaxies will have been consumed or dispersed during the long collision. Without fresh gas flowing in, the fires of stellar birth will simply cease to be kindled. Milky will keep the stars it has, tending them as they age, but it will make almost no new ones, a galaxy living quietly on what it has already been given. The gas that feeds galaxies does not come from nowhere. It flows along vast cosmic filaments, immense threads of matter stretching across the universe like a luminous web funneling material into galaxies over billions of years. But as the universe continues to expand, those filaments will stretch and thin, their flow diminishing. The cosmic web that built the galaxies we know will grow ever more tenuous, a fading architecture of matter slowly dissolving into the widening dark. Roughly 100 billion years from now, a span of time so vast it makes the current age of the universe feel like a single breath. The accelerating expansion of space will have carried every other galaxy cluster beyond the reach of Milky forever. The local group will be entirely alone, an island of light adrift in an otherwise empty cosmos. Scientists believe this isolation is essentially inevitable, written into the nature of dark energy itself. And within that island, Milky will drift on, unhurried, luminous, and alone. The Virgo supercluster, the vast structure of which the local group is just a distant outlier, will itself be undone by dark energy across unimaginable timescales. This supercluster spans hundreds of millions of light-years and contains thousands of galaxies, each one a world unto itself. But dark energy does not rest. Slowly, patiently, it will stretch the space between those galaxies until their gravitational bonds can no longer hold. One by one, each cluster will drift beyond reach, dissolving the supercluster as quietly as morning mist dissolves in open air. Within the isolated local group, Milky will not be entirely still. Its remaining dwarf galaxy satellites, small, faint companions that have orbited for billions of years, will gradually spiral inward and be absorbed. Each merger will be slow and gentle by cosmic standards, a quiet drawing together rather than a violent collision. Over immense stretches of time, Milky will gather these smaller companions into itself, growing incrementally, the way a river slowly widens as tributaries find their way home. Imagine a traveler in the far future, standing in whatever passes for night in that distant era, looking outward from Milky into the sky. They would see almost nothing. No neighboring galaxies scattered across the heavens, no distant spirals glimmering at the edge of sight. Only Milky itself, and perhaps a handful of small satellite companions, would remain visible. The sky would be extraordinarily dark and still, a profound, unhurried emptiness surrounding a single island of light, like a lantern burning alone in the middle of a vast, calm sea. Long ago, early astronomers called galaxies island universes, isolated worlds of stars separated by unimaginable distances. In our own time, that is only a poetic idea, because telescopes can still reach thousands of other galaxies across the observable sky. But in the far future, it will become literally and completely true. The accelerating expansion of space will carry all other galaxies beyond the cosmic horizon, the boundary beyond which no light can ever reach us. The island universe will be real and total and permanent. Over trillions of years. Timescales that make the current age of the universe seem like a single heartbeat. The stars within Milky will exhaust their nuclear fuel, one by one. Each star burns by fusing lighter elements into heavier ones, and that fuel is not infinite. Slowly, across unimaginable spans of time, the fires will begin to go out. Not all at once, not with any drama, but quietly and individually, the way candles in a great hall are extinguished one at a time as the evening grows late. Let your body settle a little more deeply now. There is nothing to hold on to, nothing to figure out, nothing that needs your attention. Just the slow rise and fall of your breathing, steady and even. Let your shoulders release. Let your hands rest open and still. You have traveled far tonight, through billions of years and billions of light years, and all of it has brought you here to this quiet moment. There is nothing left to do but let go and drift and rest. Even as Milky ages and dims, its most massive stars will not go silently. The heaviest stars burn brightest and die fastest, and when they go as supernovae, brilliant, brief explosions that seed the surrounding space with heavy elements forged in their cores. Iron, calcium, gold, and 100 other elements scatter outward into the galaxy. Even in Milky twilight, these rare fleeting deaths will enrich the fabric of the galaxy, leaving behind the raw material for whatever forms next, long after the stars themselves are gone. Stars of middling size, like our own sun, end their lives in a quieter and rather beautiful way. As their hydrogen fuel runs low, they swell and brighten, then shed their outer layers in a slow luminous cloud called a planetary nebula. What remains at the center is a small, dense, glowing core called a white dwarf. These nebulae are among the loveliest structures in the cosmos, translucent shells of glowing gas, each one a soft farewell, drifting outward through the dark like a lantern released into still water. After a white dwarf forms, it no longer generates energy through nuclear fusion. It simply radiates the heat it already holds, cooling gradually over tens of billions of years. Like an ember pulled from a fire, it dims slowly, from white to yellow to orange to red, until at last it fades into something dark and cold. Scientists call this final stage a black dwarf, a dense, inert remnant, no longer glowing, resting silently in the dark. The cooling is so unhurried, so measured, it is almost like a long, untroubled sleep. Here is a quiet and remarkable thing. The universe has not yet been alive long enough for a single black dwarf to exist. The cooling process takes longer than the current age of the cosmos. Every white dwarf that has ever formed is still glowing, still warm, still somewhere in the middle of its long, slow fade. The first black dwarfs will not appear for an almost incomprehensible span of time yet to come. In this way, the universe is still very young, still in the early hours of a story that will unfold across durations we can barely name. Red dwarf stars, the most common stellar type in the universe, burn hydrogen so slowly they can live for trillions of years. They are small and dim, barely a fraction of the sun's mass, and because of that, they are extraordinarily frugal with their fuel. Where a massive star burns through its reserves in mere millions of years, a red dwarf sips and sips, sustaining itself across timescales that dwarf the current age of the cosmos many times over. They are the quiet, patient ones, the long-burning embers of the stellar world, unhurried and enduring. The very last naturally burning star in Milky will be one of these tiny red dwarfs, shining on for up to 10 trillion years after everything else has gone dark. 10 trillion years, a number so vast it dissolves all ordinary sense of time. The universe as we know it is less than 14 billion years old. This final star will outlast that age by nearly 1,000 times over, and yet it will simply glow on, small and steady, a single point of warmth in an otherwise lightless galaxy, until at last even it exhales its last and goes still. When that final star fades, Milky will enter what scientists call the degenerate era, a long, dark age populated not by living stars, but by their remnants, white dwarfs cooling in the dark, neutron stars spinning slowly down, black holes resting at the centers of ancient orbits, no fusion, no warmth, no new light being born. The galaxy will not vanish. It will simply become a vast, silent collection of things that were once stars, drifting through the dark together, the way old ruins persist long after the civilization that built them has passed. Among the wanderers of this dark galaxy will be brown dwarfs, objects too small to ever ignite as true stars, drifting through the void in enormous numbers. They are sometimes called failed stars. Though that name feels a little unkind, they simply never reached the threshold needed to begin fusion. They formed, they cooled, and now they drift. Dark, dense, unhurried, like smooth stones resting on the floor of a deep and lightless sea. There will be vast numbers of them, silent companions to the remnants, moving through the dark on their own long, unhurried paths. Of all the objects remaining in this post-stellar galaxy, neutron stars and black holes will be the most energetic. Neutron stars, the crushed cores of exploded massive stars, still rotate, still pulse, still carry the memory of the tremendous forces that made them. Black holes hold the concentrated gravity of entire collapsed stellar lives. They do not glow the way stars do, but they are not passive either. They warp the space around them, pull passing matter into tight orbits, and wait. In the long dark of the degenerate era, they are the last truly dynamic presences, quiet but powerful, like deep currents moving beneath a still surface. Very occasionally, across the immensity of this dark era, two stellar remnants will drift close enough to collide. When two neutron stars meet, or a neutron star spirals into a black hole, the result is a kilonova, a brief, brilliant flash of light and energy that illuminates the surrounding darkness for a moment before fading away. These collisions forge gold, platinum, and other heavy elements in an instant of extraordinary heat. They are rare and fleeting, like a single match struck in a vast, dark room, a moment of brightness that lingers in the mind long after the flame has gone out. There is nothing you need to hold on to right now, nothing to remember, nothing to figure out, nothing left undone that cannot wait until morning. Let your body settle a little more deeply into wherever you are resting. Feel the weight of your limbs, the warmth beneath you, the slow and steady rhythm of your own breath. Each exhale carries a little more of the day away. Each breath in brings something quieter, something softer. You are here, you are safe, and the whole vast universe is simply drifting on around you, unhurried, immeasurably wide, and at peace. Over timescales almost impossible to hold in the mind, spanning 10 to the power of 19 to 10 to the power of 20 years, gravitational interactions will slowly eject most of Milky's remaining stars and remnants out into intergalactic space. One by one, over unimaginable stretches of time, objects will be nudged and jostled by the gravity of their neighbors until they reach escape velocity and drift away forever. The galaxy will not explode or collapse. It will simply thin out, like a crowd that disperses so gradually no single moment of departure is ever noticed. The mechanism behind this dispersal is not a dramatic one. It is simply the accumulation of countless small gravitational nudges exchanged during close encounters between passing objects over vast stretches of time. Each encounter is subtle, a slight tug here, a gentle deflection there, but across durations longer than the current age of the universe repeated billions upon, these interactions add up. Some objects gain energy and drift outward, others lose it and fall inward. The whole process is patient and statistical, the way water shapes stone, not through force, but through the quiet persistence of repetition. As the outer remnants of Milky are gradually flung away into the dark, the central black hole grows. Those objects that lose energy in gravitational encounters do not escape. They fall inward, drawn toward the center, and are eventually swallowed. Over these extraordinary timescales, the supermassive black hole at Milky's heart will steadily accumulate mass, growing larger and more dominant as the galaxy around it empties out. It is a slow and inexorable process, the last great gathering, pulling the scattered remnants of a once brilliant galaxy back toward its quiet, lightless center. Eventually, only the central supermassive black hole and a sparse halo of cold remnants will mark where Milky was. The galaxy that once held hundreds of billions of stars, that blazed with supernovae and hummed with the slow turning of spiral arms, will have been reduced to a single dark mass and a thin, scattered cloud of cooling objects drifting around it. No light will come from within. No new stars will form. Only the black hole will remain, immense, patient, and alone, a kind of memorial written in gravity, where a galaxy once shone. Hawking radiation is the theoretical process by which black holes slowly evaporate by emitting thermal radiation. According to this idea, the quantum nature of space means that even the empty vacuum near a black hole's edge is not truly empty. Pairs of particles flicker into existence, and occasionally one falls inward while the other escapes. Over time, this steady, almost imperceptible emission carries energy away from the black hole. The process is extraordinarily slow and extraordinarily faint, but it is continuous, and given enough time, it would drain even the most massive black hole completely. Stephen Hawking proposed black hole evaporation in 1974, weaving together quantum mechanics and general relativity in a single remarkable insight. It was one of the most celebrated theoretical results of the 20th century, a moment when two great pillars of physics, which rarely speak to each other, were brought into brief and beautiful contact. Hawking was in his early 30s when he arrived at this conclusion, working through mathematics that most physicists found astonishing. The results suggested that even the darkest objects in the universe carry within them a kind of slow, inevitable unraveling. A black hole with the mass of the Sun would take about 2 times 10 to the 67th years to evaporate through Hawking radiation, a number so large it bears almost no relationship to any duration the human mind can feel. Written out, that number would stretch across more pages than there are atoms in the observable universe. And yet, it is finite. It is a real duration, with a real N. Even something as seemingly permanent as a stellar mass black hole is, in the deepest sense, temporary, a slow exhalation lasting longer than any word we have for time. Milky's final supermassive black hole, carrying the mass of billions of suns, would take around 10 to the power of 100 years to evaporate through Hawking radiation. That duration is so far beyond the evaporation time of a stellar mass black hole that the two figures are barely comparable. The black hole would persist long after every other process in the universe had ceased, radiating away its mass in the faintest possible whisper of energy across a span of time that has no analogy in anything we know. It would be the last object in the universe to let go. The number 10 to the power of 100 is called a googol, a name that sounds almost playful for something so staggering. The current age of the universe is roughly 14 billion years, a number that already strains the imagination. A googol is larger than that by a margin that no metaphor can adequately bridge. The evaporation of Milky's black hole would not simply outlast the universe as we know it. It would outlast it by a factor that makes the entire history of cosmic time feel like the briefest of opening moments, a single soft note before a silence of unimaginable length. As the black hole evaporates, it does not fade at a steady, uniform rate. The process accelerates. As mass is lost, the black hole radiates more intensely, which causes it to lose mass faster, which intensifies the radiation further. For most of its existence, the emission is so faint as to be essentially nothing. But in the very final stages, the process rushes toward completion, ending in a brief, brilliant release of energy. The last moments of a black hole that has endured for a googol years would conclude in a sudden outpouring of gamma rays, a final, fleeting flash after an almost eternal silence. There is nothing you need to think about right now. Let the numbers and the distances and the vast stretches of time simply drift past you like clouds. No need to hold them, no need to understand them fully. Just let them pass. Feel your body resting where it is, heavy and warm and still. Let your breath come and go on its own, without effort, without direction. You are somewhere safe and comfortable, and the universe is going about its slow, unhurried business all around you. You can simply be here. You can let yourself go. After the last black hole evaporates, the universe enters what physicists call the dark era, a phase in which no remaining energy sources exist anywhere. No stars, no stellar remnants, no black holes radiating their last warmth. The universe will be filled only with an extraordinarily diffuse sea of photons and particles, all at nearly identical, vanishingly low energies. Nothing will drive any process. Nothing will change in any meaningful way. It is not darkness as we experience it, the absence of a light that was recently present, but something far more complete, a stillness that has no memory of what came before. Proton decay, if it occurs, would dissolve ordinary matter on timescales of around 10 to the 34th years. Protons are the building blocks of atomic nuclei, the foundation of everything we can see or touch, and current physics suggests they may not be permanent. If they do decay, then even the cold remnants of white dwarfs and neutron stars that survived the stellar era would eventually come apart, their matter dissolving into radiation and lighter particles. The rocks, the metals, the frozen remnants of worlds, all of it would slowly, silently unravel. Nothing made of ordinary matter would remain. If protons decay, even the cold white dwarfs and neutron stars will eventually disintegrate into radiation and leptons. The white dwarfs that cooled over trillions of years, the dense neutron stars that endured through the long stellar twilight, all of them built from protons, all of them subject to the same slow unraveling. Given enough time, every remnant of the stellar era would dissolve. The iron, the carbon, the oxygen, all of it would release back into the universe as diffuse radiation and the lightest of particles. Quietly, without witness, the last solid things would cease to be. The Big Freeze scenario predicts that the universe will approach maximum entropy, a state physicists call heat death. Entropy is a measure of disorder, and the universe, over immense timescales, tends always toward greater and greater disorder. Every star that burns, every particle that decays, every photon that travels moves the universe incrementally in this direction. The Big Freeze is not a violent ending but an almost imperceptible settling, the universe growing more uniform, more spread out, more evenly distributed, until nothing anywhere differs from anything else. In heat death, no thermodynamic work can be extracted anywhere in the universe. All processes cease, and time itself loses meaning. Work requires a difference, a hot place and a cold place, a high energy and a low energy, somewhere for something to flow. In heat death, no such differences remain. Every region of the universe rests at the same vanishingly low temperature. No engine can run, no chemical reaction can proceed, no thought can form. Time, which we experience as change, would have nothing left to measure. It would not be an ending so much as an eternal, undisturbed sameness. The fate of the universe ultimately depends on the nature of dark energy, which remains one of the deepest mysteries in all of science. Dark energy is the name given to whatever is driving the universe's accelerating expansion. But beyond that name, we understand very little about it. We cannot see it, touch it, or measure it directly. We know it exists only through its effects on the largest structures in the cosmos. Scientists believe it makes up roughly 68% of everything that exists, and yet it remains, in a very real sense, completely unknown. It is a mystery held gently, with wonder rather than worry. Dark energy was discovered in 1998, when observations of distant supernovae revealed that the universe's expansion is not slowing down, but accelerating. Two independent teams of astronomers were studying a particular type of stellar explosion, one that always burns at a known brightness, to measure cosmic distances. What they found astonished the scientific world. The most distant supernovae were fainter than expected, meaning the universe was expanding faster than anyone had predicted. The light from those ancient stellar deaths, traveling for billions of years, carried within it the first evidence of a force reshaping the entire cosmos. If dark energy strengthens over time, a scenario called the Big Rip could tear apart galaxies, stars, atoms, and space-time itself. In this possibility, the force driving expansion would grow without limit, first pulling galaxy clusters apart, then individual galaxies, then solar systems, then planets, then molecules, then atoms, and finally the very fabric of space. Each scale of structure would be overwhelmed in turn, the universe unraveling from its largest forms down to its smallest. Scientists believe this remains only one of several possible futures, not a certainty, but a quiet reminder of how much still lies beyond our understanding. The Big Rip, if it occurs, would happen in roughly 20 billion years, placing it before most of the long stellar evolution described in the ages that came before. This means the slow twilight of red dwarfs, the cooling of white dwarfs, the evaporation of black holes. All of that would only unfold if the Big Rip does not intervene. The universe's story branches here into futures we cannot yet read. What we know is that 20 billion years is still an almost incomprehensible distance from now, longer than the current age of the universe. Whatever comes, it arrives with extraordinary patience. A cyclic universe model proposes that a big crunch could one day reverse the expansion and trigger an entirely new Big Bang. In this vision, the universe does not end but transforms, contracting back toward a single point of unimaginable density, then rebounding outward in a new beginning. Each cycle would erase the memory of the one before, replacing it with a fresh cosmos, new laws perhaps, new structures, new possibilities. It is a profoundly restful idea in its own way, not an ending, but a turning, the universe breathing out and then, after an eternity of stillness, breathing in again. Let yourself settle a little more deeply now. There is nowhere to go and nothing to resolve. Let the breath come slowly, and let the body grow heavier where it rests. The mind can wander, if it likes, through galaxies, through futures, through the long, unhurried silence between stars. Or it can simply rest here, in the warmth of this moment. You have traveled a long way through time tonight. You have seen the beginning and the middle, and the many possible ends. Now there is only this, the quiet, the stillness, the soft edges of sleep drawing close. Let them come. The ekpyrotic model suggests our universe is one of many vast membranes, brains, as physicists call them, drifting through a higher dimensional space, periodically colliding with one another to restart cosmic history. In this picture, what we call the Big Bang was not a beginning from nothing, but the collision of two such membranes, releasing an enormous burst of energy that filled our universe with matter and radiation. Each collision erases what came before and sets a new story in motion. Our entire cosmos, with all its galaxies and stars and long, slow futures, may be just one chapter in a story told across dimensions we will never directly see. Regardless of which future unfolds, merger, rip, freeze, or cycle, the disappearance of the Milky Way as a distinct and recognizable galaxy is considered essentially certain by astronomers. The details of how and when may vary across models, but the broad conclusion holds: this spiral structure, these arms, this particular shape of light we call home, will not endure forever. There is something quietly settling about that certainty. It is not a loss so much as a transformation, the galaxy not gone, but changed beyond recognition into something else entirely. The very word galaxy carries the memory of how our ancestors first saw this river of light overhead. It comes from the ancient Greek phrase meaning milky circle, a name given to the pale, luminous band that arched across the night sky, long before anyone knew what it truly was. In that simple phrase, you can hear a people looking up in wonder, reaching for language to hold something vast and beautiful. They called it Milky. They called it a circle. And in doing so, they gave the entire universe one of its most enduring words. Long before telescopes, the great thinkers of ancient Greece turned their minds toward that luminous band and debated its nature with care. Some believed it was a phenomenon of the atmosphere, a kind of celestial vapor or residue clinging to the upper air. Others argued it must belong to the heavens themselves, something beyond the reach of earthly weather. They had only their eyes and their reasoning, and yet they asked exactly the right questions. That willingness to wonder, to look up and ask what is that, is perhaps the oldest form of science there is. In 1610, Galileo turned his small telescope toward the Milky Way and saw something no human eye had ever resolved before. Not a cloud, not a vapor, but individual stars, countless points of light, packed so densely they blurred together into a continuous glow. With a single observation, the ancient debate was settled. The Milky Circle was made of stars. What had seemed like a soft smear across the sky revealed itself as a vast multitude, each point a sun in its own right. The universe, in that moment, became immeasurably larger than it had been the night before. In the 1780s, the astronomer William Herschel undertook a remarkable project. He and his sister Caroline set out to count and map the stars visible through their telescope, attempting to determine the actual shape of the galaxy from within it. Night after night, they recorded the density of stars in different directions across the sky, building a rough but pioneering chart of the Milky Way's structure. Herschel's map was imperfect. He did not yet know about the dust that dims distant stars, but the ambition was extraordinary. For the first time, a human being tried to draw the galaxy from the inside. In 1923, Edwin Hubble made one of the most consequential measurements in the history of human knowledge. By identifying a particular kind of pulsing star, a Cepheid variable within the Andromeda Nebula, he calculated its distance and found it lay far beyond the boundaries of the Milky Way. Andromeda was not a cloud of gas within our galaxy. It was an entirely separate galaxy, millions of light-years away. The universe, which many had assumed was essentially the Milky Way, turned out to contain countless other such systems, each one an island of stars adrift in an ocean of space. The scale of what Hubble revealed is still difficult to fully absorb. Before his discovery, the universe as humanity understood it was essentially one galaxy, our own. After it, the cosmos expanded overnight into something almost beyond conception. Hundreds of billions of galaxies, each containing hundreds of billions of stars, spread across distances so vast that light itself takes billions of years to cross them. The light entering your eyes from Andromeda tonight left that galaxy more than 2 million years ago, before our earliest ancestors had yet learned to shape stone. Hubble did not just change astronomy. He changed the size of everything. Tonight, more than 1/3 of all people on Earth cannot see the Milky Way from where they live. The glow of cities, streetlights, and screens has washed the night sky into a permanent amber haze, erasing the very galaxy our solar system calls home. For most of human history, the Milky Band overhead was simply part of life, as familiar as the seasons. Now entire generations are growing up beneath skies where it is invisible, without ever knowing what has been lost. The galaxy is still there, unchanged, arching overhead, but the darkness needed to see it has quietly slipped away. Light pollution is not holding steady, it is growing. Each decade, the artificial brightness of the night sky increases, and the number of people who can see the Milky Way with their own eyes quietly shrinks. Children born in cities today may never look up and see the galaxy their own sun belongs to. There is something tender and a little sorrowful in that thought that the oldest sight in human experience, that river of light overhead, is becoming a rarity, not because the galaxy has changed, but because we have surrounded ourselves with so much brightness that we can no longer see into the dark. Let the breath come slowly now, and let the body settle a little deeper into wherever you rest. There is nothing left to hold on to tonight, no question waiting for an answer, no task left undone. You have traveled across billions of years, from the first light of stars to the long silence beyond them, and now the journey is drawing gently to a close. Feel the weight of your limbs, the warmth of the air around you. Let thoughts drift as they will, growing lighter and more distant, like stars seen through softening eyes. The universe is vast and unhurried, and so is sleep. Let it come. From a dark sky site, far from any city, the Milky Way reveals itself as a luminous river of light, flowing from horizon to horizon. Standing beneath it, you feel the full weight of belonging to something ancient and immense. The band shimmers with layered depth, bright clouds of stars, dark lanes of dust, faint wisps of nebulae, woven together into one continuous, unhurried stream. It asks nothing of you, it simply shines. Across the world, certain lands have been set aside as dark sky preserves, places where artificial light is carefully limited so that the Milky Way remains visible overhead. These protected parks and reserves exist not only for scientists, but for anyone who wishes to look up and see what every human generation before the modern age took for granted. They are a quiet act of care, a promise to the future that this ancient site will not be entirely lost. The Milky Way does not stand fixed overhead. It rises and sets with the turning of the seasons, shifting its position across the sky as Earth journeys around the Sun. The dense, glowing heart of our galaxy is best seen from the southern hemisphere during its winter months, when the galactic core climbs high above the horizon in a blaze of warm amber and violet. In the north, it appears lower, softer, a subtler presence threading through summer nights. Astrophotographers venture out into the darkest corners of the world, setting up cameras on tripods beneath open skies, opening their lenses wide and letting light gather for minutes at a time. A long exposure collects what the eye alone cannot: the full sweep of the Milky Way's arch, the delicate gradations of color within its dust lanes, the faint tendrils of nebulae threading between the stars. Each image is a collaboration between human patience and the slow generosity of starlight. Radio telescopes listen to the Milky Way in wavelengths the human eye will never perceive. Among the most revealing is a faint signal emitted by clouds of hydrogen gas at a wavelength of 21 centimeters, a whisper that passes freely through the galaxy's dust, carrying a map of its structure. By tracing these hydrogen signals across the sky, astronomers have charted spiral arms hidden behind veils of interstellar material, assembling a picture of our galaxy's shape from the inside out. Infrared light passes through dust, the way a warm glow filters through closed curtains, softened but not stopped. The Spitzer Space Telescope, designed to see in infrared wavelengths, used this quality to peer through the Milky Way's dense dust lanes and illuminate the spiral arms hidden within. What had been an obscured interior became, for the first time, a legible map. The galaxy's true shape, its sweeping arms, its central bar, emerged from the haze like a face slowly coming into focus. Since its launch in 2013, the Gaia Space Telescope has been performing a task of extraordinary patience, measuring the precise position, distance, and motion of nearly 2 billion individual stars within the Milky Way. Each measurement is a tiny thread in an immense tapestry. Woven together, they form the most detailed, three-dimensional portrait of our galaxy ever assembled, a living map of stellar motion that will take decades of study to fully understand. The light leaving your eyes tonight has been traveling since long before Gaia began its quiet watch. For many years, textbooks described the Milky Way as having two primary spiral arms. But when Gaia's precise stellar measurements were analyzed, a richer picture emerged. Our galaxy carries 4 major spiral arms, each a long curving river of stars and gas winding outward from the central bar. The revision was not a correction of an error so much as a deepening of understanding. The galaxy had always been this way, waiting for instruments precise enough to read it clearly. The James Webb Space Telescope peers so deeply into the universe that it sees galaxies as they existed billions of years ago, when the cosmos was young and still assembling itself. Among those distant shapes, astronomers have found galaxies that resemble the early Milky Way, small, irregular, rich in gas, blazing with newborn stars. Looking at them is something like finding an old photograph of a place you have always known, the same essential nature, but younger, rougher, full of unspent energy. Every photon of Milky Way light that reaches a human eye tonight has been traveling for thousands of years. It left its star long before any written record existed, crossing the silent dark of the galaxy at the speed of light, until at last it arrived here, at this moment, at these eyes. The galaxy is not a distant abstraction. It is a living message, arriving continuously, patient and unhurried, from a past so deep it dissolves the boundaries between then and now. Let your body grow heavy now, sinking gently into whatever holds you. There is nothing left to do tonight, nothing to solve or remember. Let each breath come a little slower than the last, and with each exhale, release a little more of the day. The thoughts that drift through your mind need not be followed. Simply let them pass, like clouds moving across a still and open sky. You are here. You are resting. All is well. The light arriving from the galactic center tonight began its journey about 26,000 years ago. It left the heart of the Milky Way long before the first cities rose, before the first fields were planted, before the earliest written word was pressed into clay. It has been crossing the silent interior of the galaxy ever since, unhurried and unwavering, until at last it reaches this small blue world and rests, for a moment, in the dark of a human eye. When you look up at the Milky Way on a clear and dark night, you are not seeing the galaxy as it is, you are seeing it as it was. The light painting that pale river across the sky left its stars thousands of years before a single word of recorded human history was written. Every civilization that has ever risen and fallen on this earth did so beneath a sky whose light had already been traveling toward us for longer than memory reaches. The galaxy you see is a portrait of the deep past. Every star you see tonight is a message from the past. The nearest ones sent their light years ago, the farthest ones centuries or millennia before that. The night sky is not a single moment, but a vast collage of moments, each arriving from a different depth of time, all reaching your eyes at once. To look upward is to stand at the receiving end of an unimaginably long chain of light, a quiet correspondence between the universe and the one small creature willing to look. The Milky Way will never truly vanish without a trace. Long after its spiral arms have dissolved, long after its name has been forgotten, the stars that once composed it will persist, transformed into white dwarfs, cooling slowly across trillions of years, or scattered into the vast dark between galaxies, still carrying within them the atoms forged in ancient stellar cores. The galaxy disperses, but it does not disappear. It becomes something quieter, something more diffuse, something that continues. When Milky has long since settled into its final elliptical shape, the heavy elements born inside Milky Way supernovae will still be cycling through the universe. The carbon, the oxygen, the iron, forged in stellar furnaces billions of years ago, will pass from star to planet to atmosphere to ocean, through chemical reactions and biological forms we cannot yet imagine. The Milky Way's gift to the cosmos is written not in its shape, but in the periodic table it helped to build. The iron flowing through your blood right now was forged inside a star that died before our solar system existed. A supernova somewhere in the early Milky Way released that iron into space, and over millions of years it drifted and condensed, and eventually became part of the dust cloud that formed our sun and earth, and, in time, you. You are not merely living beneath the Milky Way. You are, in a very literal sense, made of it. The galaxy did not just surround your ancestors, it built them. The Milky Way is not a backdrop to human life, it is the source of human life. Every atom of calcium in your bones, every atom of oxygen in your lungs, every carbon molecule threading through the chemistry of thought and memory, all of it was processed through the interior of Milky Way stars before it ever became part of you. The galaxy is not something you look at from a distance. It is something you carry within you, quietly, in every cell, with every breath. On the night the Milky Way finally dissolves into Milky, there will be no human eyes to witness it, no voice to name what is lost, and yet nothing will truly be lost. Every atom that ever made up a Milky Way star, every heavy element forged in its supernovae, every particle that once drifted through its spiral arms, all of it will continue, woven into whatever forms the universe finds next. The galaxy does not end. It transforms, and somewhere in that transformation, in matter that was once a star, once a world, once a living thing, the Milky Way will persist, quiet, unhurried, and eternal. Sleep now. Let the stars keep watch. You are made of something very old and very enduring, and tonight, that is more than enough. Good night.